Okay, looking at example number 2, we just finished this. Let's move forwards and look at another example. Before we do that, let's look at the idea of what similar triangles is all about. So we're going to start at the beginning of this page once again and get started here. Now, similar triangles, the proof of these is somewhat similar to congruent, but it has some special features that you need to be aware of. For example, the symbol for similar is a tilde, the little squiggle. The squiggle represents that the two triangles are similar, but they're not exactly the same. What it means is that the two triangles are the same shape, but different sizes. And the corresponding angles are equal in both triangles, but the lengths of the sides of the triangles, so the lengths of the corresponding sides, are proportional. So rather than them being equal, they're actually proportional. So here's an example of two triangles that have the same angles on the inside, just as you see here. You see a marked angle right here. You see the star and an O, and again, a marked, a star, and an O. And so these two triangles are actually similar. They're similar that BAC, so again, BAC is similar to FGE. That means that you have corresponding angles that are equal. For example, B and F are equal, A and G are equal, and C are equal. So angle B is equal to angle F, angle A is equal to angle G, and angle C is equal to angle E, but their sides are actually proportional. So what I'm doing down here, you'll notice, is that I'm naming all the sides of the first triangle mentioned. So triangle BAC, all the sides. There's AB, AC, and BC. And they correspond to sides on the other side. They're not equal to those sides, but they are proportional, meaning that AB, it compares to GF. AC compares to GE. And finally, BC compares to FE. All of these proportions is equal to some value. We're going to talk about it in a little bit. Now note the angles. Up until now, I have not allowed you to use single letters. And to be honest, it's probably not a good idea. So let's name angle BF with the 3 letters. So ABC is equal to angle GFE. BAC is equal to angle FGE. And finally, ACB is equal to angle GEF. All right, and here's that K value right here that you see here. This K value listed here, this is the number that is equal, regardless of which sides I divide, it is equal to some scale factor, K, that we're going to talk about and probably in the next little while. Now, conditions for similarity. In order for two triangles to be similar, they can be side, side, side similar, which means that 3 pairs of the corresponding sides are directly proportional to 3 pairs. So 3 pairs of corresponding sides are proportional. So that means they compare to each other, just like we had the K factor in the previous example. And we'll see more examples of this. So here's one given to you, 1, 2, 3, and 3, 6, 9, given the letters A, B, C, D, E, F. Now, AB over and BC and AC are on this side in this triangle, and we're going to compare it to this triangle. So the small side in A is AB, small side in the other triangle is DE, and then we have BC, which matches with EF, and finally the last one, AC, matches with DF. And because of that, we know that these values will all be the same. Let's see, by dividing them, you reduce them all, and they all equal 1/3. That means that because this scale factor is 1/3 and it's the same for all three, which is what it should be, what that gives you is that since all three sides are proportional, you can prove that triangle ABC is similar to triangle DEF by side-side-side similarity. So you proved it, proving that the scale factor is the same by comparing the sides. All right, another condition for similarity is side-angle-side similarity, where you have two pairs of corresponding sides are proportional, and there is one angle, the contained angle, that is equal to each other. Now I'm going to show you what I mean here. Here we go. So we have our two triangles here, A, B, C, D, E. And we have some measurements given to us. And we have to prove that these two triangles are similar. This one and this one are similar. How are we going to do that? Well, what we're going to do is compare them. 3.6 will compare with 0.9. AC will compare with EC. 3.6 over 0.9, and that gives us a number 4. Then we'll compare another two sides, BC and DC. BC and DC will compare, and that will also give us a number 4. So we have the same K factor, the scale factor, so we need a contained angle. Contained, again, guys, is this angle here. It has to be supported by the two sides. You cannot prove side-angle-side similarity or even side-angle-side congruence unless that is true. So, does angle ACB equal angle ECD? And hopefully you're thinking yes. Those are going to be equal. All right, now this is just showing that they're proportionally equal. So ACB is equal to angle ECD because of OAT, opposite angle theorem. And now, folks, we've proven side-angle-side similarity. All right. Okay, so we've proven side-angle-side similarity. Let's look at the first one, the next one. Now, keep in mind, we had congruency side, side, side. We had side-angle-side congruency as well as similarity. So these two are similar. You might be thinking that we have angle-side-angle similarity. And folks, it's a little bit different with this. We actually, in similarity, we have something called angle-angle similarity. That's right, there is no side. Because for similarity, you have to be able to compare sides with another set pair of sides. Can't really do that with one pair of sides. So similarity, we have the luxury of just having to prove two angles are equal, and therefore that will prove that the triangles are similar. So angle-angle similarity means that two pairs of corresponding angles are equal. That's all we're looking for. So let's look at an example here. Here's our example, and we need to prove that triangle ABE is similar to triangle CDE. All right, let's look at what we can do. So ABE is similar to CDE. How? Well, lucky for us, we have angle BAE is equal to angle DCE. That's given to us. Wonderful. Fantastic. Next, we have angle BEA is equal to angle DEC. Does anyone know why? Hopefully you're thinking, well, let's see. BEA, DEC, that's the same angle. It's like two triangles on top of the same angle. And that's right, that means it's a common angle. Therefore, we can state the following, that triangle BAE is similar to triangle DCE because of angle-angle similarity. Wonderful for us. Now, in general, we can use similar triangles to find missing angles or sides in different triangles. Let's look at some examples. Example 1. Find EF. So we're looking at finding EF, and this is the information that's given. BC is 48 meters, CE is 12 meters, and CD is 16 meters. What should we do first? Well, hopefully you're looking at this and saying, oh, I had better fill in the information that I'm given. BC is 48 meters, so you should write 48 here. CE is 12. CD, which is this one over here, is 16. And this is what we need to find. Well, before we can do anything, we have to prove that the two triangles are actually similar. And we can do that using a formal proof, or we can prove it by saying triangle BCD is similar to BEF because of, well, let's see, there's parallel lines here. So BCD is equal to BEF because of F pattern here. So P, parallel line theorem, F. And you could use common angle over here. CBD is equal to EBF because of common angle. Or if we wanted to, we could have done F pattern backwards over here. So definitely, there's multiple possibilities here. Ultimately, we've proven through angle-angle similarity, two angles are equal in both triangles, therefore the two triangles are similar. We can say that since they are similar, we can say that the sides are proportional. That means BC matches with BE, CD matches with EF, and BD matches with BF. Now we're going to fill in the information given to us. BC is 48. BE is 48 plus 12. That's right, 48 plus 12. CD is 16, and EF is what we need to know, EF. We don't need BD and BF. It's neither given to us nor do we need it, so we would ignore that. We only need these two values to be able to solve. So what you do is do cross multiply. You cross multiply and solve. So 48 over 60 equals 16 over EF. 48 times EF is equal to 16 times 60, which is 960. Now keep in mind we want to keep EF by itself. So we're going to take EF equals 960 and divide it by 48. We get an answer for EF of 20. That's right. Therefore, EF is 20 meters long. Okay, moving on to the next one. Example number 2. In triangle ABC, AB is equal to 9, BC is equal to 12, and AC is equal to 15. In triangle XYZ, we have YX is equal to 6, XZ is equal to 8, and angle X is equal to 90 degrees. And you're asked to show that triangle ABC is similar to triangle YXZ. So we have ABC and YXZ, and we're to now show that they are similar. Well, let's see what we can do. First of all, you'll notice that in ABC we have measurements, but in YXZ we have two sets of measurements and an angle in between. But it's a special type of angle, so you're thinking, how can we solve this? Well, hopefully you're thinking, well, if I know that this is a right angle, I can actually use a theorem to be able to find this missing side over here. And then I can use side, side, side similarity. Or, opposite to that, we could prove using that same theorem that I would use here to be able to prove that it works so that this guarantees a 90-degree angle. Either way, you will get to be able to prove that you have two similar triangles. So, let's use the way you would know from grade 9 and find a certain side. So, in triangle ABC and triangle YXZ, I know that AB and YX is equal to 3 over 2. I know that BC over XZ is equal to 12 over 8. And the beauty is we're given this statement here, so each angle corresponds to each side. Now, what's next is, because we proportionally proved it's proportionally equal, so because of that, we have two scale factors. What we have to do is try and, let's say, prove side, side, side similarity. Well, to prove that, we need the value of yz. Yz is equal to, using Pythagorean theorem, 6 squared plus 8 squared is equal to yz squared. Yz is then equal to the square root of 6 squared plus 8 squared. Again, we use Pythagorean theorem to figure that out, and that gives us 10. Square root of 100 is 10, folks. So when I compare AC to YZ, 15 over 10 also gives me 3 over 2. And guess what? It's also the same scale factor as the other two. Therefore, you've proven that triangle ABC is similar to triangle YXZ because of side, side, side similarity. Contrary to that, we could have proven that there was a 90-degree angle here by using Pythagorean theorem to prove left side equals right side, and that also would have given us similarity by using side angle side similarity. All right, last one. Example number 3. Prove that the two triangles are similar. Then find HI. So here's our two sets of triangles going on here. And you're to find HI. All right, how are we going to look at this? Well, beauty of this is we do have an angle with another angle. We do have a side. We have another side. We have, how can we prove this? If we use the side measurements, we don't have two sides over here. Because remember, you need at least two sides to be able to prove either a side angle side similarity or a side 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 similarity. So we don't have that possibility. But we do have an angle given to us, and we do know something special about these angles right here. That's right, it's OAT again. So we can prove the two triangles are similar using angle-angle similarity. So here we go. In triangle FGJ and triangle, what does FGJ connect with? Hopefully you're thinking FGJ must connect to IHJ. That's right, IHJ. And what we do is FGJ is equal to IHJ because it's given to us, and FJG is equal to IJH because of OAT, opposite angle theorem. Therefore, we've proven that FGJ is similar to IHJ because of angle-angle similarity. And now what we can do is find the value of HI. So GF is similar to HI, GJ is similar to HJ, and FJ is similar to IJ. So what do we do now? Fill in the information. GF, we don't know. We don't know GF. We need HI, so we need this one because we need to find HI, but we need GF. How would we find the value of GF? Hopefully you're thinking, that's right, Pythagorean theorem. GF will equal 6, the hypotenuse squared minus 4 squared. How do you know which side's the hypotenuse? Remember that the right angle points to the hypotenuse, and that's important to remember always, always, always. The right angle points to the hypotenuse, and therefore you know which side is the hypotenuse at all times, which is 6. So 6 squared minus 4 squared, and then the square root of that, that means GF is equal to, using Pythagorean theorem, root 20. Leave it as root 20, folks. Some of your calculators would give you 2 root 5. That's fine with me, but do not give a decimal. That is crucial. So GF is root 20. HI we don't know yet. GJ we know is GJ is 4. But we don't know HJ and we don't need it. So guess what? Even though we know GJ, we're not actually going to use GJ or HJ. We're actually going to use FJ. That's right, FJ, which is 6, and IJ, which is 18, because now what we can do is solve for HI by cross-multiplying. When we cross-multiply, we get 6 times HI is equal to 18 root 20. That means HI is equal to 3 root 20. How did you get 3 root 20? Remember, you have to divide by 6, and 18 divided by 6 is 3, and root 20 is on the inside. Your calculators will give you an answer of 6 root 5, which is fine, but ultimately the final answer that you want is a decimal. Yes, I do want a decimal in the end. So at the very, very end, you give me the decimal. That's when you touch your calculator, and you find out that HI is equal to 13.4164 meters. All right, folks, that's the end of 7.1. Take care. Have a numerical day.